Welcome to the Deep Dive, where we take fascinating information and really extract the key insights for you.
For you, the listener who's curious wants to get informed efficiently.
And maybe have a few aha moments.
Yeah.
Today, we're plunging into the really exciting world of agile-legged robots.
Yeah, how researchers are basically giving these machines the smarts to move with, well, incredible skill in messy, real-world places.
It sounds like science fiction, almost. And our guide for this is a cutting-edge research paper.
That's right, it's called Parkour in the Wild, learning a general and extensible agile locomotion policy using multi-expert distillation and RL fine-tuning from 2025.
Sounds technical, and it is, but our mission here is to boil it down. We want the essential, kind of mind-blowing parts about the future of robots that can truly go anywhere.
Exactly. We want to understand how a single brain, an AI controller, can let a robot navigate all sorts of challenging terrains nimbly, reliably.
And drawing upon a whole toolbox of learned skill.
A whole toolbox, yes.
Okay, so let's start with the basics. Why is this so hard? Why can't we just, build robots that stroll through cluttered, uneven ground easily?
Well, the fundamental issue is just the sheer unpredictability of the real world. Think about it.
Yeah.
Uneven ground, slippery bits, obstacles everywhere, all shapes, sizes. Current robot control systems, they're pretty good in the lab, controlled settings.
Right, we see those cool videos.
Exactly. But they often stumble, literally, when faced with this kind of variability. They just don't generalize well beyond what they were specifically programmed for.
Yeah, it's like that uncanny valley, but for movement. You see amazing lab feats, but then picture that same robot in a forest fire aftermath or rubble. It's a whole different ballgame.
Totally. There's this huge gap between current robot abilities and the natural agility of, say, a mountain goat, or even us walking on a rocky beach.
And the applications are huge, right? Search and rescue, space exploration, if robots could really handle that complexity.
Precisely. And, while the robot bodies, the hardware, keep getting better, the real bottleneck now is often the software.
The brains.
The brain's telling the legs what to do. We need smarter, more adaptable control.
Which brings us, I guess, to reinforcement learning. RL. Sounds like this has been a pretty major step forward.
Absolutely. RL lets robots learn through trial and error, mostly in simulation, where they can fail safely millions of times.
Like practicing over and over.
Exactly, until they figure out the best way to move. And this has led to some surprisingly robust ways to handle different kinds of tricky terrain. The paper notes several recent successes using RL for agility.
Yeah, they mentioned work from just the last couple of years showing this field is really maturing, which is exciting, but there's a catch, according to this paper.
There is. These RL-trained skills tend to be, well, very specialized, hyper-focused.
So if you teach it to climb stairs brilliantly.
It might be completely lost trying to cross a field of rocks or walk on a narrow beam.
Ah, okay. So the skills don't transfer easily.
Not easily at all, they're narrow. So the big question this research tackles is, how do we take all these individual specialized skills?
Like all the different parkour moves.
Right, and combine them into a single control system? One brain that can handle a wide variety of challenges, reusing what it learned in different ways.
And not just combine, but also add new skills later without messing up the old ones. That extensibility thing they mentioned.
Exactly. That's crucial. Extensibility. You need to be able to add new abilities as the robot encounters new situations without catastrophic forgetting, without losing the old skills.
Okay, so how did Rudin and the team actually do it? This Parkour in the Wild paper. You said it's a 3-stage process.
That's right. 3 stages. Stage 1, they train individual AI experts.
Specialists.
Exactly. Specialists for very specific tasks, like one expert for climbing stairs, another for jumping gaps, another for walking on beams, another for scrambling over rocks. They built on previous work and actually trained 9 of these distinct experts.
9 different specialists. Okay, that makes sense. Get really good at one thing first. So what's stage 2? How do you get them to work together?
Stage 2 is called multi-expert distillation. Think of it like taking the knowledge from all those 9 specialists and distilling it down, concentrating it into a single, more general student AI policy.
Like a knowledge transfer.
Pretty much. The student policy learns by watching the experts and trying to imitate them. It learns to predict which expert's behavior it should copy based on what it's seeing around it.
Okay, so the student figures out, Ah, this looks like a climbing situation. I should act like the climbing expert. Or this looks like a jump. Time for the jumping expert's moves.
Precisely. But here's a really key and challenging part: the original experts. They were trained using perfect, detailed 3D maps of the terrain, like having a blueprint.
Ah, okay. They had all the information.
Yes. But the student policy, it has a much harder job. It has to learn to make all these decisions using only images from depth cameras.
Like the kind of camera a real robot would actually have on board.
Exactly, like Microsoft Kinect or Intel RealSense type cameras.
Wow, that's a big leap. From a perfect map to just camera views. It has to figure out the terrain, even parts it can't directly see, just from those depth images.
That's the challenge. It has to infer the terrain geometry. And to help with this learning, they used a technique called Dagger. It's basically a smart way to collect data, showing the student what the experts would do in situations it finds tricky.
So it gradually learns to mimic the right expert, using only the camera feed. Okay, so experts trained, student distilled.
Yeah.
What's stage 3?
Stage 3 is reinforcement learning fine-tuning. So this distilled foundation policy from stage 2, it's good, it knows the basics from the experts, but it's not perfect.
Needs refinement.
Exactly. So they refine it further using more RL, but this time on a much wider, more diverse set of terrains, including some the experts never saw, like real-world 3D scans of rubble piles from actual search and rescue training sites.
So you take the generalist student and throw even more challenges at it to make it even better and handle totally new stuff.
That's the idea. This fine-tuning polishes its performance on the basic terrains and, crucially, lets it learn to handle more complex scenarios the individual experts weren't trained for.
And this is where that surprising behavior emerged.
Yes. This was a real aha moment, they reported. The policy, through this fine-tuning, actually started figuring out things on its own. Like, it learned to adjust the robot's body, its posture, to get a better view of upcoming obstacles with its depth camera.
Wow, it learned to look actively. That wasn't programmed in.
Nope. It emerged from the RL process trying to succeed at the task, active perception. And this stage also helps with that extensibility problem. They showed you could take the fine-tune policy and fine-tune it again on new terrains to learn new skills without significantly degrading the old ones.
That's huge. Continuous learning.
Aha.
Okay, you mentioned the perception challenge relying just on depth cameras when moving fast. Let's circle back to that.
Right. It's tough. Perceiving complex obstacles accurately during agile moves, when the robot state isn't perfectly known, it's really hard. Traditional ways of building a 3D map on the fly can be slow or unreliable.
So their solution was to feed the depth images directly into the control AI.
Yes, the policy learns to act directly from sequences of depth images.
Okay.
But crucially, to make this work reliably from simulation to the real world, they had to make the simulated camera data look really messy, like real data.
Ah, bridging the sim-to-real gap.
Exactly. They developed a very detailed noise model. They simulated all sorts of real-world camera problems, parts of the image getting cut off, noisy edges, random holes or dropouts, blind spots near the robot, even Gaussian blur.
So they degraded the perfect simulation data to match what the real robot's cameras would see.
Precisely. And they applied similar processing to the real images, too. This meant the AI trained in simulation was already used to dealing with noisy, imperfect camera input, making the transfer to the physical robot much smoother. It shows the level of detail needed.
Okay, so they did all this training, experts, distillation, fine-tuning with noisy data. Then came the tests. How did the different policies stack up?
They ran a lot of experiments. The results, especially in their Table 4, are interesting. The distilled policy, the student before fine-tuning, could do all the skills but generally wasn't as good as the specialized experts on their specific tasks, which kind of makes sense, right? Jack of all trades.
Master of none initially.
Right. But the fine-tuned policy, that showed a big improvement. Often it performed just as well as, or sometimes even better than, the original experts on their own turf.
Wow.
And importantly, it generalized much better to complex new terrains it hadn't seen during the initial expert training, like that parkour line and the scanned rubble meshes it only saw during fine-tuning.
So the fine-tuning really paid off, making it both proficient and adaptable. What about completely unseen terrains, stuff it never encountered in any training stage?
Results there were more mixed. It did reasonably well on some, but struggled on others, which, highlights the limits. True generalization to anything is still the holy grail, but it showed real promise.
Still, impressive progress. And they did that experiment showing it could learn a new skill later.
Yes, the repeated fine-tuning test. They took the final policy and fine-tuned it specifically on one tough terrain, climb down on stones. Performance on that task shot way up, and crucially, performance on all the other tasks barely dipped.
So it learned the new skill without forgetting the old ones. Extensibility confirmed.
Exactly. It demonstrates a path to continuously adding capabilities.
They also compared this whole distillation plus fine-tuning approach to other ways people have tried combining skills, right? Like hierarchical control.
They did. And their findings suggested that their method worked better, especially with this larger number of skills, nothing in this case, and for generalizing to new situations. Other methods, like hierarchical control or using something called a VAE for encoding skills, seem to struggle more with scaling up or adapting robustly.
Interesting. And another key element you touched on was memory, using a specific type of neural network, an LSTM.
Yeah, they showed that was critical. They compared using an LSTM, which has memory, to a simpler network, an MLP, which doesn't. The policy with memory performed vastly better.
Why is memory so vital here?
Well, think about it. The robot only sees a snapshot of the world from its camera at any instant. To understand how the terrain unfolds, how obstacles relate to each other, and how its own movement affects what it sees, it needs to remember the recent sequence of images.
Like putting together frames of a movie to understand the action, rather than just seeing disconnected photos.
Exactly. Without memory, it's much harder to make sense of the dynamic environment from just depth images, especially during fast motion.
Okay, and back to that emergent behavior, the active perception. The robot adjusting its posture to see better.
It's really fascinating. Figure 8 in the paper shows this. The fine-tuned policy learned, on its own, to tilt the robot's body to improve the camera's view of obstacles. It wasn't told to do this. It emerged as a useful strategy for navigating better.
That hints at a deeper level of intelligence developing, beyond just mimicking.
It really does. It shows the power of letting these policies optimize for the task in rich environments.
So all this simulation work, these clever training techniques, did it actually work on a real robot?
Yeah.
The ANOI Moldy?
Yes, the real-world deployment. That's the ultimate test, right? And the paper reports it was a major success.
What did they do?
They put the final fine-tuned policy onto the physical AMI MALD robot and tested it in real indoor and outdoor environments, including search and rescue training facilities with rubble piles the robot had never seen before.
Wow.
And it worked remarkably well. The robot, using just its onboard depth cameras, navigated these complex, unstructured terrains. It performed dynamic motions, adapted to the messiness, and was pretty robust.
Robust how? Like, if things went slightly wrong.
Yeah, they mentioned it handled things like slippery ground, its feet getting momentarily caught, even visual distractions without completely failing, which is vital for real-world use.
That sounds incredibly promising. A single AI learned through this process, driving parkour-like skills in the real world. Were there any limitations noted?
Oh, sure. They acknowledged it wasn't perfect. Occasional missteps still happened. And they noted a tendency for the robot to use its knees a bit more than ideal during climbs and jumps, suggesting areas for refinement in the reward functions or training. But overall, a big step
A
forward.
really significant one, yeah.
Okay, let's try to wrap up this deep dive then. What are the core takeaways for you, for our listeners?
I think the main point is this three-stage pipeline. Train experts, distill their knowledge, then fine-tune with RL in diverse settings. It seems like a really powerful and, importantly, scalable way to build general locomotion skills for these robots.
Taking the best of specialized knowledge and blending it into an adaptable, improving generalist. Exactly. And the fact they achieve this using only onboard depth cameras, handling all that noise and uncertainty, that's a huge practical step. It gets us closer to robots that can actually operate autonomously in the messy, unpredictable environments where we might need them most.
Absolutely. This research really feels like it's pushing the boundaries, bringing those sci-fi visions of highly mobile robots a bit closer to reality.
It really does. And it makes you think, doesn't it? What are the broader implications here? If robots can learn these complex physical skills through AI, how far can this go?
What new possibilities open up? For exploration, for assisting people, maybe even for understanding how animals and humans learn to move.
Yeah, some really big questions to ponder.
Definitely food for thought. Well, thanks for taking this deep dive with us today. If this sparked your curiosity, keep exploring. There's always more to learn.